All right, let's talk about something that trips up pretty much everyone in machine learning at some point: overfitting. You know that feeling, right? You build a model, it looks absolutely perfect on paper, and then it just completely bombs in the real world. So, what is actually going on?
Have you ever been Alex? I think we all have. You've built your model, the training accuracy is through the roof, you're thinking, I've nailed it. And then the second it sees new data, it just falls apart. This isn't just a random fluke. It's a classic symptom of a very specific problem.
And this problem, it has a name. It's called overfitting. And at its core, it's all about the difference between a model that has truly learned a pattern and one that has just, well, memorized the answers to the test. Let's really break that down. Okay, so that's the formal definition. But what does it really mean? It means your model is the student who gets a perfect score on the homework because they copied the answer key, but then completely flunks the final exam. It's gotten so good at the exact data it was trained on that it can't handle anything new. It hasn't learned the underlying rules, it's just memorized the examples. I love this student analogy because it just makes so much sense. The overfitting model is that memorizing student. They're brilliant if you ask them the exact same questions from the practice sheet, but they're totally lost if you just change the numbers a little. Our goal is to build the other student, the one who gets the core concept and can apply it to any problem. That's what we call generalization. Now, behind all of this is a really fundamental idea in machine learning called the bias-variance tradeoff. You can think of bias as having a model that's way too simple, that's underfitting. But variance, that's our troublemaker today. Variance is the error you get from a model that's too complex. It's so sensitive that it starts learning the random noise in your data. That's why overfitting is a high variance problem. And our job as engineers is to find that perfect sweet spot right in the middle.
Okay, so we know what overfitting is, but how do you spot it in the wild? And what causes it to happen in the first place? Let's take a look.
Overfitting usually creeps in when your model is just too powerful for the amount of data you're giving it. Maybe you've got tons of features, but only a handful of examples. Or you're using something like a decision tree and you're letting it grow as deep as it wants. You know, even just training for too long, running too many epochs can cause a model to go from learning the signal to just memorizing the noise.
And this right here, this is your number one warning sign. Going back to Alex's problem, that 26-point drop between training accuracy and test accuracy is a massive red flag. A tiny gap is fine, that's expected. But a chasm like this, it's basically your model screaming, I don't know how to generalize.
Here's another fantastic way to catch it. Watch your error rates while you're training. If you see the training error going down, 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 which feels great, right? But the error on your separate validation set starts to flatten out or even creep back up, stop right there. That's the exact moment your model switched from learning to just memorizing. Now, the good news is we are not helpless here. There is a whole toolkit of powerful, proven strategies that we can use to fight overfitting and build models that actually work in the real world. So let's open up that toolkit. Your first line of defense always should be a really solid validation strategy. Instead of just one simple train test split, something like k-fold cross-validation makes your model train and test on several different slices of your data. This gives you a much more honest, much more reliable picture of how it's actually going to perform. Next up, one of my favorites, regularization. This is a brilliant technique where you essentially add a penalty to the model for becoming too complex. It's like telling the model, hey, try to explain this data, but keep it simple. It forces the model to use smaller, simpler parameter values, which makes it way harder to overfit. For linear models, the two big ones you'll see are L1 and L2. The key difference to remember is that L1, also called Lasso, is so strict it can actually shrink some feature weights all the way to 0, basically doing automatic feature selection for you. L2, or Ridge, is a little gentler. It shrinks all the weights to be smaller but doesn't usually eliminate them, which is great when you think all your features have at least some importance. And there are so many other tools in the box. Honestly, getting more data is often the best cure of all. You can also manually remove features that are just adding noise, start with a simpler model to begin with, or use early stopping to halt the training right at that sweet spot we talked about. And of course, there are ensemble methods like random forests, which are fantastic because they fight overfitting by their very nature, averaging out a bunch of different models. So, theory is great and all, but let's see how this stuff actually works with a quick practical example. So here's our showdown. In one corner, we have a decision tree that's allowed to be as complex as it wants, a classic recipe for overfitting. And in the other corner, we have a regularized tree, where we've put some constraints on its complexity. Which one do you think is going to do better on brand new data?
And look at these results. It's so clear. The unconstrained tree looks like a genius on the training data, hitting 99% accuracy. Amazing, right? But on the test data, it plummets to 75%. That massive gap is the overfitting we've been talking about, plain as day. You just can't trust this model.
Now, check out the regularized tree. Yeah, the training accuracy is lower, it's 87%, but look at the test accuracy, 85%. The gap is tiny. This model actually performs 10 points better in the real world. This is what we're aiming for. It learned the general pattern, not the specific noise.
And this really brings us to the most important point of all. When we're building these things, what's the actual ultimate goal we should be chasing?
This quote from Maya, as senior data scientist, just says it perfectly. A consistent, reliable model is always more valuable than a flashy one that only works in the lab. Our goal is not to get the highest score on the training set. Our goal is generalization.
So the next time you're building a model and you see that super high training score, I want you to stop and ask yourself this question. Is my model truly learning the patterns, or is it just a really, really good memorizer? Don't be fooled. Dig deeper, use the tools we talked about, and make sure you're building a great learner.